Hello and welcome back to another video with ItsDrDan, and today we're going to be learning about orbital diagrams, which is going to further illustrate how we can show electron configuration in a more visual manner. The big reason why we need to learn about this is because with electron configuration, it can get a little confusing. But there are three major rules for how to actually be able to make sure you are filling everything in correctly in order for us to go by. The big reason is when you have a periodic table and you're trying to read it to actually assign where electrons go, it's a little hard. So the first rule is the Aufbau Principle, which is we always fill our lowest energy level first. So we start at the bottom and we go all the way up to the top, meaning we start at the 1s orbital, move up to 2s, then to 2p, and so on, filling as we go. Now, being that every orbital has so many, or every essentially sublevel has so many orbitals available, one thing we got to keep in mind is we can only fit 2 electrons in every single orbital. Okay, so when we are doing those 2 electrons, why 2? Well, you got to think this electron is this little subatomic particle. The way to look at it is think of it as like a ball. So if I have, let's say, a basketball and I was trying to spin it on my finger, well, what direction could you actually spin it? Well, the one way to think of that is it can either spin either counterclockwise, or you could try to, or sorry, clockwise or counterclockwise when you are trying to do that. So it's all about which direction will this thing rotate on when it's rotating around its axis. So this is the whole idea of spin. So when we are writing these in orbitals, we'll show orbitals as a little line, and we are going to show the electrons as arrows. So one of them is going to be going up, and the other one is going to be going down to represent spin up, as we call them, and spin down. Okay, so now this is an oversimplification of the idea, but it's just enough for us to be able to understand this concept rather than diving deep into the quantum mechanics and understanding how these all work. Now, the last rule is Hund's rule, which is essentially when you are writing your electrons in these orbitals, some of the orbitals are considered to be degenerate. Now, what is a degenerate one? Well, an example of this would be, let's say if I had the p orbital. So p has 3 individual orbitals to it. It has one on the x-axis, one on the y-axis, one on the z-axis, if you're to try to think of this mathematically. So when we are trying to fill our electrons in this, we fill 1 electron in each individual orbital first before we start pairing them up. Now, the reason behind this, but while we're pairing them up, is essentially it comes to the analogy I love to use is, let's say you are to try to stay in a house with a bunch of roommates. Do all of you start kind of jamming everybody into just one bedroom inside the house? Usually not. Generally, you all want your own private space, your own private room. Then you start doubling people up when you run out of space. So when it comes to like the p orbital, right, you can only fit up to 6 electrons, but you're going to start putting somebody in each bedroom first before you start filling up everything. Okay, so and then once you've run out of room, you then go to the next floor and start filling that up as well. Starting off, let's start off strong. What does this entire picture look like? Well, right here, what I have shown is essentially a complete orbital diagram for an atom that could have, let's say, it had the maximum number of electrons possible. Every single one of these orbitals is all the ones possible in your periodic table. So you can see on the far left in yellow, we have S, in purple, we have P, and then in blue, we have D, and then F we have in green. Now, with these, it's a very common question that you get asked on homeworks, is in order to either draw these or to try to list them in order. Now, keep in mind, we're always going to have our little rules that are here with us, right? The first thing is, how do you decide where do electrons go in this entire mess? Well, remember, rule number 1, the Aufbau Principle. electrons always start in their lowest level. So one way to help you try to remember how to start this is use the diagonal method. So the diagonal method, this is a chart that you can download anywhere on the internet. If you look up diagonal method for electrons, you'll find it. You can find it in any textbook. The way it works is it's written in a very specific order. Notice how every single row has the same quantum number. Now, keep in mind, you're doing diagonal, meaning how we're going to show this. We'll start in the corner. We go up, right? So 1s2 would be first. We then go to 2s2. We do that one up, and we keep doing diagonals across to show how all these are done in order. So we go from tails to heads. All right. So just to kind of illustrate how does that work. So if you look at how I started it, right, I went 1s2, then I went to here, right, so tails, up to 2s2, then I went to 2p6 to 3s2, then to 3p6, then to 4s2, 3d10, and so on, right? We can show how that order is as we are representing this based on what we are seeing here, right? So we can write down the entire thing as far as we need to put that order based on the diagonal method. And this can keep going all the way through the entire thing to complete that picture. So using the diagonal method is a really, really easy way to remember this. Now, keep in mind, most professors and teachers do not give you this on exams. So it's something that you kind of got to memorize how to put it together. Just keep in mind, right, that these are all going by their individual rows of that periodic table. All right. So when you are going through these, we're going to be filling them in, and let's go through some actual examples for how we can fill in those electrons using arrows to show it. The first example is nitrogen. So nitrogen, the electron configuration is 1s2, 2s2, 2p3. So what does all this represent? Well, if you remember from my previous videos on electron configuration, we learned that we could find these and write them based on our periodic table. We're just learning how to put them in orbital diagrams. First thing is all those exponents, they're representing the total number of electrons that are here. So we have 7 total electrons. Now, the way that we're going to put them in our table here is being that we have 1s2, that's going to be our first orbital. So we're going to put 2 electrons in 1s2, right? And notice how I did spin up, spin down. So we first followed our Aufbau Principle by starting at the lowest level. And then we did the Pauli-Exclusion Principle, which is all about them pointing in opposite directions. Now, being that we just did that one, what we do next is 2s2. So we go up, down, like so, and then we will continue that trend. So being that now we have 2p3, well, we don't just automatically write all 6 electrons. We now got to use Hund's rule, which we have degenerate orbitals here. So we're going to assign each electron gets their own room, okay? So being that you have 3 rooms available, why not put an electron in each one first? And when we do this, they all point in the same direction, either all pointing up or all pointing down. You choose as the artist, they all got to be pointing in the same direction. And one thing you can check for yourself is, do you have 7 arrows, right? So you can kind of see here, I have 1, 2, I have 3, 4, and then I have 5, 6, 7, right? So I have all of my arrows here. We can also use the count valence electrons really easily as well. If you remember, valence is your outermost shell. So everything that is in the 2 group here, which is your highest quantum number, is your valence. So that means in this case, we have 5 valence electrons and 2 core electrons for this example. Let's go on to the next. Sodium is 1s2, 2s2, 2p6, 3s1. So now what we are going to be doing is filling in our orbitals once again. So we first start with 1s2. We are going to put our 2 electrons into that orbital. They're now accounted for. We'll go on to 2s2, which is now our next lowest energy level. We will fill in both of those. We will move on to 2p6, then to 3s. And as a result, remember, we're filling one electron in each orbital first because of Hund's rule. Now we're going to come back and fill in the remainder because we have, as you can see, we have 6 electrons in that orbital. So we're going to put all 6 in there as we go. Then for 3s, we only have one single electron. Being that's the lowest possible available, we will put one electron in that level, just like so. Now this is a orbital diagram for sodium, okay? We can also still do the little math too for ourselves. How many valence electrons do we have? So once again, you're going to look, what is your highest level? So we have 3 here. That is your highest one. So we have 1 valence electron across all the other electrons here. So you can see we have a total of 11 total electrons, but one of them is in your outermost level. So phosphorus, we're going to do the same general idea. We're going to start from the bottom. So we start at 1s, and we're going to put our first 2 electrons in. And notice how it's a pattern, right? We're going in the exact same order every time. So 1s2, 2s2. So we have both of those completed. Now we're going to go to 2p6 and to 3s2. So we're following Aufbau Principle by doing the lowest first. And we're also doing Pauli-Exclusion Principle by doing the opposite spins. Notice how we're doing Hund's rule by filling in the whole orbital first. Then we do our S. Okay, now so 3p. So notice how we have 3p3. So how should we fill this in with Hund's rule? Well, keep in mind, being that these are all degenerate orbitals when we have our p orbital. So we're going to put essentially one individual in each room first for phosphorus. And this is how we do an orbital diagram for phosphorus. We go through and we fill in one at a time until we don't have any electrons left. And we can even go through and count them as well, right? You can see there's a total of 15 electrons for this atom. So 15 total. And we can see that we have 5 valence electrons available. Let's go on to our next example. Okay, so sometimes a more realistic example that you might have to come across is writing the orbitals from scratch where they're not there for you, which can prove to be a challenging problem. But we have the diagonal method here. So how exactly can you do this? Now, depending on your examples that you have, you don't always have to write this in order of going from bottom to top, showing the energy levels. Sometimes you can also write them in like from left to right horizontal as well, as long as you're labeling and showing how does the energy increase. So in this case, an example, if I want to go from left to right, we're going to do the same thing as before. We start at the 1s, and we are going to write those 2 electrons in 1s. Next, we have 2s, so we'll write our 1 orbital for 2s, put our arrows. We'll go to 2p and then 3x. Now at 2p, we have 3 orbitals here, 1 in each going across. And then 3p5, we will fill 3 across and then come back with 2 electrons. Now, looking closely at this one, what are some things to notice in terms of counting the electrons? Another thing to talk about is paired and unpaired electrons. So one thing you can see is that there are many paired electrons here. So anything that's paired is when you have 2 electrons going up and down. Unpaired is when you have a lonely electron that's by itself in a room. So for this particular example, we have 1 unpaired electron. Okay, so there's many different ways. Now, one of the things when you have an unpaired electron, it generally means that that atom will have a tendency to either want to lose electrons to get rid of it, or to gain electrons to get rid of it. They don't like having lonely electrons. They all want to have a partner. So for this one, I want to look at chlorine minus, right? So chlorine as an anion, or if you remember, anions are negative, meaning that we are going to be gaining an electron. So how would that happen? What's going to occur is if you have a cation or anion, you're going to edit your electron configuration. So we notice here how it changed from 3p5 to 3p6. this shows the gain of 1 electron. So that's also going to change in the electron configuration, and it's going to change over here in the orbital diagram too. So we'll add an extra arrow to represent, oh, we now have chlorine, and it gets rid of that unpaired electron, making it paired. Okay, so that's something else that can be done as well. So a couple little tricks here that are possible to have, and we're still following all our rules as we go through it. So let's take a look at a few more examples and see what else we can do as well. For this example, we are going to do scandium, and particularly we're going to look at the scandium 2+ cation. So how do we go about it? Well, let's first just draw the neutral one first, and then we will fill in the rest of the puzzle. So we're going to use our diagonal method to help us. So being that this is a very useful little trick. So first things first, right? We fill in our lowest orbital, do that Aufbau Principle. So we do 1s, and then 2s, and then 2p6 will be next. And then we will do 3s2. Now you can, so we did the first few. So now we're going to be doing 3p6 to 4s, and then into the 3d orbital. So let's fill in all of our electrons. All right, now being that we have scandium 2+, where do we take the electrons? So how exactly does this work? So when we have a cation, where the electrons are going to be taken from the outermost layer. Now, what is your outermost layer? This is from your valence electrons. So cations lose valence electrons first. Okay, so that's very, very important to remember. We lose the valence first. So what are your valence electrons in this case? Well, it's not 3D, believe it or not. It is the 4s electrons are your highest level, right? It has the highest quantum number, meaning they're the ones on the outside layer. So being that when we do this for our configuration, we are going to take away the electrons from 4s. Even though it was written earlier, it still had the higher number. So that's going to go away, and we're going to take that out and erase it, okay? And it's only going to have 3d1. So we'll remove those electrons from that orbital, leaving it empty as a result, okay? So they disappear first. And that's because 4 is greater than 3, okay? So 4 is a greater atomic, or not atomic, quantum number than 3. All right, let's take a look at another weird, quirky rule. So this is known as the exception rule. All right, our last example is about the exception rule. So there are some exceptions to how electron configuration and orbital diagrams can work in terms of the periodic table. There's 2 exceptions that can be found, and it's on the column with chromium and the column with copper in your periodic table. So the chromium and copper families. So let's say if we look at the first one, which is chromium. So I wrote its noble gas configuration here, which is 4s2, 3d4. Now, if you kind of notice with the degeneracy here, well, I wrote we have 4 electrons by itself, and we have these 2 electrons over here that are together. Well, it doesn't seem like there's anything bad, but there's one thing that these have a tendency to want to do. Notice how there is this empty room all by itself. And these 2 guys over here, these 2 brothers, have to share a room. Well, it's like, oh, I can move upstairs and have my own room. That's what is actually going to happen. So with this, let's kind of change the colors here a little bit. We can have where one of these electrons is actually going to end up moving over here to this other level. Now, all 6 electrons here all have their own individual orbitals all to themselves. So the configuration is going to change as a result. It's no longer going to be a 4s2 3d4. Instead, we're going to have argon 4s1 3d5. So this only happens at the chromium and copper row. So copper is the same idea. So notice how I have 4s2 3d9, We're also going to have it where instead it wants to do 4s1, 3d10. So let's try to take a look at that. So it's these elements on here on the periodic table. So the one thing to keep in mind is you never ever want to write S2D4 or S2D9. So maybe like put on a flashcard for yourself. If you see yourself writing it down, that is one of the exception rules. So it's these 5 elements here. So it's chromium's column, if you remember it that way, and copper's column. It's an easy way to notice it, being that it's at the 9th spot and the 4th row. It's the only time these happen. It's very common to get chromium or copper on an exam or a homework, and you have to be aware of the exception. All right, so this is all of orbital diagrams. Thank you so much for listening. I hope that this video helped you a little bit. Try to understand a little bit more of electron configuration. How do we draw electrons? How can we try to actually put them in their own unique boxes? And there'll be more content to come. Thank you so much. Please hit that like and subscribe button if you haven't yet. And I will see you all later. Bye now.